Can somebody confirm that you can hear me?
I
I
can hear
can.
you.
Thank you. I think we have a little bit of chapter one to finish. We'll open up chapter two just in case. All right, before we begin, are there any questions? Here doesn't quite look right. Let's see. Should be seeing my screen now. Remember to send in your topic. Your topic must be approved by me. If it's not approved by me, you're just going to get a -10 deduction. So before you uh, work on your infectious disease project, remember to get it approved by me. There's several people who I've narrowed the topics down, and there's a few people who I've told that that's not an infectious disease. So, all right, today is April 17th, 2 days after tax day, and we're supposed to be on chapter two. We're a little bit behind schedule. Any question about any of that? All right, let's begin chapter one. I have that we had discussed the normal microbiota, where you can find it on a person. So the normal microbiota do not normally cause disease. However, they can cause disease in certain circumstances, such as a AIDS patient. They have no immune system, and the normal microbiota may cause disease in cases like that. Another example would be a cancer chemotherapy patient. Their immune system is weakened by the chemotherapy, and the normal microbiota may cause disease in them. Whenever the normal microbiota is not growing where it should be, it can cause disease. Like E. coli is normally found in the gut of an individual, but if it's found in the ear or in the lungs, it will be causing disease. So, an infectious disease results when a pathogen overcomes the host resistance, and an infectious disease is caused by a pathogenic microbe. A pathogen is a microbe that can cause disease, and it has certain properties that allow it to cause disease. Remember, most microbes do not cause disease. An emerging infectious disease is a disease which is new or changing, that is increasing or has the potential to increase in incidence. Can anyone name an emerging infectious disease at the moment?
COVID.
Ebola.
COVID-19 would be an emerging infectious disease. I don't think there's any cases of Ebola at the moment. Somebody could maybe look that up or Google it. But um, Ebola might have the potential to increase in incidence, so I don't know if it's considered an emerging infectious disease or not. Ebola has been around since around 1970, and it was probably around before that. We just didn't know about it. But another one that is a potentially emerging infectious disease is the bird flu. There's concern that the bird flu at the moment does not spread very easily from person to person. And if it were to become airborne, it could easily spread from person to person. And the bird flu is highly toxic if a person gets it, meaning it has a high lethality rate. So there is concern that the bird flu may have the potential to increase in incidence, and so it's an emerging infectious disease. That's all you need to know about an emerging infectious disease, and that's the definition. I do have more slides about emerging infectious disease, but you will not be held accountable for these slides, and they're just for your own information, meaning I don't ever talk about emerging infectious disease. Any question about any of that? All right, that's it for chapter 1. Any questions on chapter 1 before I close it down?
Will this be uploaded today?
Remind me after the, well, maybe I can do it right now. If I'm at that spot, I'll do it right now. If I'm not at that spot, I'm not at the spot. So remind me um, later today and I'll upload it. All right, where do we have chapter 2? There we go. Chapter 2, as is normal, I gave you an introductory slide telling you the major goals and a rough outline. So obviously, always know the terms of a chapter. What's an organic compound? What's an inorganic compound? What are hydrocarbons? What are polar and nonpolar molecules? What are hydrogen bonds? What are acids? What are bases? And what is the pH? Now remember, to know all of the goals, you have to come and take a look at the objectives for chapter 2, which you can find, I think I have it in the objectives for chapter 2. Yep, overview and objectives. So you can find all of the goals, which are the objectives, in chapter 2. And there's the study guide. Now I'm right here. Let's see if I can get chapter 1 posted. All right. The lecture notes for chapter 1 are now online. And then 2, meaning in the next item is, with respect to the 4 major biological molecules, be able to describe the relationship and the characteristics of the monomers and the polymers, be able to describe the composition, structure, and function of each of the 4 major biological molecules, and then give examples of each. What are the 4 major biological molecules? These are molecules that are only found in something that is alive or was once alive. You can find 3 of them on any box of cereal or any food item. So what are the 4 major biological molecules? Come on, you should have had that in Biology 160. Well, what do you find on a box of cereal? All right, you guys need to look at a box of cereal. We're going to move on. The scale of things. For this chapter and for the next chapter, you do need to understand the scale of things. Let me see if I can blow this up. So you need to know that the largest object about that we're going to talk about is a human. Obviously, an elephant or a whale are bigger than a human, but in this graph we have the human. And then the next largest thing would be something like a chicken egg. That is the largest cell that all of you have probably seen, and that's the yolk of the chicken egg. Now, if anyone has ever seen the yolk of a turkey egg or the yolk of an ostrich egg, that would be even larger. I've never even seen the yolk of an ostrich egg, so I'm not sure if I've seen the yolk of a turkey egg, but anyways. And then a frog egg, the yolk of a frog egg is the largest cell that we can see about with our human eyes. So these things you can see with the human eye. Things smaller than a frog egg, you have to use a microscope to see. And we have the eukaryote cell. 10 times smaller than that is the cell of a bacteria. And smaller than that, the smallest thing we have would be the mycoplasma, the smallest bacteria. That's about the smallest thing you can see with a light microscope. Viruses, which isn't exactly true, but most viruses you cannot see with a light microscope. There are the very largest viruses that you could actually see with a light microscope. We'll talk about viruses much later in the term, but most viruses you cannot see with a light microscope. To see a virus, you would need to use, at least most viruses, you would need to use an electron microscope. And then smaller than a virus would be a large, excuse me, a large molecule like a protein or a lipid. And you have to realize a virus is more than just one protein. It's usually several proteins as well as uh, a genome of DNA or RNA. So a virus is larger than a protein. And then a small molecule is smaller than a large protein molecule, and that would be something like water, a small molecule. And then smaller than that is an atom. So you don't need to know the sizes of these things, but you should know the relative order, meaning a human would be bigger than a chicken egg, bigger than a frog egg, bigger than an eukaryote cell. We're talking about the average eukaryotic cell, bigger than a bacteria cell, etc. Any question about any of that? And I should point out there's an error in this picture, and that is it has 1 micrometer here and 1 micrometer there. This is an error, right? That should be 1 millimeter. And my next chapter slide, I've actually corrected this. All right, chapter 2, important molecules, especially biological molecules. We're going to talk about what organic compounds are and what inorganic compounds are. Organic compounds typically are structurally complex compared to an inorganic compound, which are simple. Uh, Organic compounds tend to be held together by carbon atoms, and carbon is important because carbon combined to 4 other atoms. And it's usually the carbon backbone which makes the organic compound, meaning the carbon bonds are what's holding the organic compound together. The organic compound is held together mostly by covalent chemical bonds, so that when 2 carbons are joined together, they're joined by a chemical covalent bond. Inorganic compounds typically lack carbon, although not all of them do. They are required by living organisms for the organism's growth, repair, maintenance, and reproduction. Some examples of an inorganic compound would be water, oxygen, and then carbon dioxide. And you know, carbon dioxide is an inorganic compound that has carbon in it, obviously. And then one of the most important molecules in a person or any living life form is water. And it is one of the most important and the most abundant molecules in a living organism. And it's an inorganic compound. Any question about any of that? Sorry, I've got a frog in my throat. I don't have any water here. Water is extremely important molecule in life in general, as well as the planet Earth. I imagine in the universe too, but uh, water is a polar molecule. What is a polar molecule? A polar molecule is one held together by a chemical covalent bond holding the hydrogen to the oxygen, but the electrons in the chemical bond are not shared equally by the oxygen and the hydrogen. The electrons in that chemical covalent bond are pulled towards oxygen and spend more of their time with oxygen than they do with hydrogen. This makes the hydrogen have a partially positive charge and the oxygen a partial negative charge. The partial charge is not a term that your textbook author uses. I think he calls it a slight charge. What I'm referring to is that the oxygen does not have a -1 charge. Okay? It is less than a -1. I'm not sure what it is exactly, but it's some fraction. Any question about any of that? So an individual water molecule is held together by a chemical covalent bond, which is a polar bond, holding the hydrogen to the oxygen inside the water molecule. But between water molecules, especially liquid water molecules, there are hydrogen bonds holding the two water molecules together. And that is the oxygen has a partial negative charge, the hydrogen has a partial positive charge. That makes an electrostatic attraction between the hydrogen and the oxygen, and that we call a hydrogen bond. It is not a chemical covalent bond. It is a hydrogen bond being held together by the partial positive charge on the hydrogen and, the partial negative charge on the oxygen. So water has two chemical bonds inside the body of water, liquid water at least, and that is within the water molecule. It has a polar covalent chemical bond. Between water molecules, at least in liquid water, it has a hydrogen bond. Any question about any of that? All right, let's watch the little video. Try and get that to load. May stop the hand. Oh, there it goes. We might get a commercial first. So that's two hydrogen gas molecules. That's an oxygen gas molecule. This is water, two water molecules. The hydrogen has a partial positive charge, both of them. The oxygen, a partial negative charge. And that forms the hydrogen bond between them. Now you'll note that the hydrogen bond can break and reform. That's because it's a very weak bond. And in liquid water, actually, let me see if I can demonstrate that. In liquid water, the reason why we have liquid is because that hydrogen bond is breaking and reforming all the time. So hopefully you can see this. I'm pouring some liquid water into here, and the water is being held together in a liquid form and can change its shape to fit the container because the hydrogen bond is breaking and reforming all the time. And that's what we have in liquid water, where the hydrogen bond is breaking and reforming all the time. And that's why water, when it's a liquid, has the properties of a liquid, where it will take the shape of its container. Any question about any of that? Whenever the hydrogen bond totally breaks, we do not have liquid water anymore. We have gaseous water, and you don't have a liquid, obviously, if it's a gas. And that's because gaseous water does not have a hydrogen bond binding two water molecules together to form the liquid. And then if you lock that hydrogen bond in place and it never breaks, you don't have liquid water either. You have solid water that we call gas, not gas, that we call ice. So solid water, the ice does not take the shape of the container because the hydrogen bonds are locked in place and they don't move. And if the water molecule cannot move around, the ice cannot change its shape to fit the size of the container it's in. And that's why it's a solid. Any question about any of that? All right. Water is a good solvent. All polar molecules and all ions can dissolve in water. A polar molecule would be something like water, and it will have a charge in the molecule. Let me go back. So it would be another molecule other than water, but it'll have a partial charge, partial positive charge on one end of the molecule, and a partial negative charge on the other end of the molecule. Obviously, water is a polar molecule. Uh, Glucose, at least when it's dissolved in water, would be a polar molecule where the hydrogens in an OH group and the glucose would have a partial positive charge, and the oxygen, at least in the OH groups, and the glucose would have a partial negative charge. Any question about any of that? So glucose would be another polar molecule. And glucose can dissolve in water. You all know that when you dissolve your sugar or your, well, sugar in your tea or your coffee, assuming you have sugar in your tea or coffee. Ions can also dissolve in water. Like here we have a salt crystal. Salt is composed of sodium ions with a positive charge and chloride ions with a negative charge. And then they're just attracted to each other. And if you ever look at actually, maybe I can get one here. Let's see if I still have it here. I don't. I can get it here though. This will be a smaller one, the trouble. And that is I have salt here. Yeah, these are really small, so I doubt you can see it very well. But the salt is being held together by the -1 and the +1 charge, and that makes the crystal making a little square shape or rectangular shape crystals of salt. And I was hoping I had the big salt crystals there, but I don't have it here. So um, anyways, that holds the crystal together. Just a -1 charge on the chloride ion and a +1 charge on the sodium ion. And water can come up to this crystal, and then for the positive sodium ion, the oxygen will be attracted to the +1, and a bunch of water molecules will come up, surround that positive sodium +1, and then take it into solution with the oxygen facing the positive +1 sodium ion. Remember, the oxygen is only a partial charge, but it'll be surrounded by several water molecules like this, and then the positive sodium +1 ion will come into solution. And the same thing with the negative chloride ions. A bunch of water molecules will come up, surround the chloride ion, and then break it out of the crystal, bring it into the liquid water, and that's how we get salt water. The difference is the -1 chloride ion, so -1, will be surrounded by the partial hydrogens, and so the water molecule will orient so that a partial positive hydrogen will be next to the -1 chloride ion. Any question about any of that? And that is how a ion, a crystal of ions will dissolve in water. And that's how we get salt water with the uh, positive plus one sodium ion being surrounded by water, and the negative one chloride ions also being surrounded by water, with the difference being the oxygen will be next to the sodium ion and the hydrogens will be next to the chloride ion. Any question about any of that? All right. Water is a good solvent because polar molecules are hydrophilic, meaning a polar molecule likes to be dissolved in water. Hydrophilic means it dissolves in water. Literally, hydrophilic means hydro water, philic lover. So it means that a polar molecule loves being in water and will dissolve in water. And glucose is a hydrophilic molecule. Sodium chloride, salt, is also a hydrophilic molecule. Any questions about any of that? Now, not all molecules are polar. Some of them are nonpolar. And non-polar polar molecules are repelled by water. The term used is hydrophobic. Hydro meaning water, phobic, fear of water, like oil and butter are hydrophobic. And although they don't really fear water, what they do is they do not dissolve in water and they will be repelled by water. So you mix oil and water together and you shake it up to make your salad dressing. The oil will separate from the water. I think everybody knows that. And that's because oil is hydrophobic. It will not dissolve in water. Any question about any of that? All right. Oops, I'm on the wrong page here. So hydrogen bonding between water molecules makes water excellent at buffering the temperature. Those of you who are used to living in Western Oregon or Western Washington know that our temperature is buffered by the Pacific Ocean. Water absorbs a lot of heat before it becomes heated and or evaporates. So water, unlike most substances, can absorb energy in two ways. First, uh, when you raise the temperature of something, what you're doing is you're putting in energy, and that energy is causing the molecule to move and vibrate faster and more. So as you raise the temperature of water, part of the energy is actually making the molecule simply move around more rapidly, and that is a measure of the temperature, meaning the temperature is how rapidly the molecules are actually moving and vibrating. And the lower the temperature, the less the molecule is moving and vibrating. At absolute zero, I think that's absolute Kelvin, the molecule is not moving at all. And that's a really, really cold temperature. And I don't know what the hottest temperature would be. Something like the temperature of the sun, where the molecule is just moving around very rapidly, and the molecule at the surface of the sun may have enough energy to leave the sun. And obviously, the sun has a lot of gravity, so it tells you how fast the molecule is moving. Anyways, that's one way that water and all other molecules can absorb energy. And that is when they take in the energy, that energy is used to increase the speed and vibrations of the molecule, and that will increase the temperature of the substance. Any question about that? All right. The other way that water can absorb the energy that most other molecules cannot is water can absorb, liquid water can absorb the energy by breaking the hydrogen bond holding the liquid water molecules together. And that will absorb some of the energy, and that energy is not taken up by the water molecule to vibrate and move faster. So that energy does not increase the temperature of the water. And then furthermore, the water molecule that absorbs the most energy, breaking its hydrogen bonds, so this will be the water molecule that has the most energy, that water molecule will leave the liquid water molecule and evaporate, meaning that the hottest water molecule will leave the water. And that evaporation will help keep the water temperature from rising. Any question about any of that? So as water evaporates, it takes the energy away from it. And so the water molecule with the highest energy, the one that will break the hydrogen bonds, will be the water molecule to leave. And that means water is actually very good at evaporating and keeping something cool. And in addition, it means that water is very good at buffering the temperature. So if you give a certain amount of energy to water, some of that energy will be taken in by the individual water molecules to make the water molecules move and vibrate more rapidly, and that will increase the temperature of the water. But some of the energy will be taken in to break the hydrogen bonds, and that will not increase the temperature of the water. And that's why water is excellent in buffering the temperature, because if we give the same amount of energy to the same amount of oil, oil will only take the energy to um, increase the speed of the oil molecules moving, and that will increase the temperature of the oil. So if you give the same amount of energy to oil and water, the oil will raise further in its temperature than the water. Any question about any of that? And there are not very many substances other than water that buffer the temperature, meaning it has two ways to split the energy that's coming into the water. Most other substances, when you simply give energy to it, it will only increase the molecules' movement and vibration, which will increase the temperature. Any question about any of that? All right. So water is excellent at buffering the temperature. Water can also split into hydrogen ions and OH. That's the hydroxide ion. And this is a hydrogen plus one. And the OH is an OH minus one, meaning this is a complete charge, not a partial charge, and that's a complete charge. Water, remember, is H2O, and it can split into from H2O into H plus and OH minus with a complete charge. Now that's water at the surface of the Earth can break into H plus and OH minus. On the surface of the sun, the water molecule will have enough energy that H2O can split into two H pluses and an OH, no, an O minus 2. That does not happen on the surface of the planet Earth because the water molecule will not be given enough energy to break the water into hydrogen and oxygen. Any question about any of that? So don't tell me that water breaks apart into hydrogen and oxygen because that doesn't happen on the planet Earth. It only happens on the surface of the sun. Water breaking into H plus and OH minus ions is important because the charged molecules can participate in chemical reactions, and that too gives water some of its properties. Actually, the hydrogen ions in the water give the water its pH. And so if water molecule initially breaks apart, one water will break into OH minus and H plus, and that will be a pH 7, which is pure water. When water first breaks apart, it'll be pH 7 because the H plus ions equal the OH ions in solution. And pH 7 is neutral, pH neutral. If you have increasing H plus in solution, where there's more positive H plus ions in solution than negative OH minus 1 ions in solution, we have increasing acidity, where the pH scale changes from pH 7 and drops to lower than pH 7, such as pH 6, pH 4, pH 2, pH 0. Any question about in that? On the other hand, if the pH goes higher than pH 7, then we have more OH minus 1 in solution than we have H plus 1 in solution. And as you get more OH minuses in solution than H plus in solution, we become increasingly more and more basic, and that can also be called increasingly more and more alkaline. Alkaline and basic mean the same thing. So pH 7, increased pH 8, a little over pH 8 is actually the pH of seawater from the dissolved minerals in the seawater. Seawater is a little bit alkaline. Milk of magnesia, a little higher than pH 10. Household ammonia, a little higher than pH 11. Household bleach, a little higher than pH 12. Oven cleaner, that would be the highest pH anyone has probably ever used, higher than pH 13. Lime water is the very highest pH. You can't get higher than pH 14. And I don't remember why you can't get higher than pH 14. pH 0, I do know why you can't get lower than pH 0. Obviously, urine, pH 6, slightly acidic. Wine and tomato juice, more acidic. pH 4, grapefruit juice, more acidic. pH 3, lemon juice. pH 2, the most acidic substance most of us have ever used. Stomach acid is actually more acidic, about pH 1.5 up to about pH 2, depending on what you ate. The most acidic thing you've ever come across would be the acid in your car battery, and that's less than pH 1, almost pH 0. At pH 0, all of the water, H2O, will split into H plus, meaning there is no more H2O, it's all H plus. And the OH minus has to be absorbed because at pH 0, there's only H plus in solution. There is no OH minus in solution. Any question about any of that? So I know what pH 0 is. pH 14, I imagine there's no H plus in solution. It's all OH minus, but I'm not sure what the definition of pH 14 is. I'll have to look that up someday. Any question about any of that? All right, the acid-base balance. Organisms need to maintain a fairly constant balance of cellular acids and bases to remain healthy. And we have buffers in our blood, for example, like H2CO3 and H plus CO3, which would have like sodium H plus CO3, which help buffer our blood. And we need that because, like I said, if you have a child jugging Coke, I used to have a picture of that. Coke is acidic, and he needs to have buffers to prevent from dying. Because if you were to eat or drink or chug too much Coke, it's fairly acidic. I don't know, pH 4 to pH 3, something like that. And you cannot have your blood go from pH close to a little over 7 down to pH 3 because that would kill you. But the child who chugs the Coke has buffers, and that maintains the pH balance in his or her body. Any questions about that? There was a term that you should have learned in Biology 160 that's called homeostasis. Not something you need to know for microbiology, but it is a term you should be familiar with. pH is actually the amount of H plus ions in solution. So when we're talking about the pH, we're talking about the amount of hydrogen ions in solution. Like the pH of 7 means we have a certain number of H plus ions in the water. And pH 6, we have another number of H plus ions in solution. The pH is exactly equal to the negative log of the concentration of H plus in solution. And I'm sure that doesn't mean a lot to you, but that's exactly what the pH is. Let me explain to you what pH 7 equals. So let's go right here. pH, oops, pH equal to 7, and I'll get this bigger in a minute here. Yeah, let's get it even bigger. There we go. So pH 7 means that for, let's go like that. For one H plus ion, how do I word this? Let's come on over here and go for 1 times 10 to the 7. We'll get that in a minute. Water molecules, which is H2O. Yep. One of them will change into H plus ion. And then there will, of course, be an OH minus. Now, let me get those right. And I can do a subscript. So for 1 times 10 to the 7th water molecules, one of those water molecules will break apart, and then we'll have one H plus ion in solution for 1 times 10 to the 7th water molecules. That's pH 7. So there's one hydrogen ion per 1 times 10 to the 7th water molecules in solution. Any question about any of that? Let me change that. Now for pH equal to 6, up, that's not right. You just do this whole thing here and I'll change it. For pH equal to 6, for 10 to the 6 water molecules, we have one H plus ion in solution, meaning the H plus concentration is 10 times more because we have one H plus ion in solution for 1 times 10 to the 6 water molecules, whereas before we had one H plus ion in solution for 1 times 10 to the 7th water molecules. Any question about that? And for pH equal to 5, same thing. Put it on that sign. You have one H plus ion in solution for 1 times 10 to the 5th water molecules. Any question about that? And then for pH equal to 0, just to show you that I actually know what I'm talking about when I said earlier, for pH equal to 0, Oop. For one water molecule, let's go there. That's 1 times 10 to the 0 is one water molecule. You have it changing into one H plus molecules. Any question about any of that? And then the same with increasing pH. Let's go over here. pH equal to 8. One times 10 to the 8th water molecules, meaning 10 times more water molecules. You have one H plus ion in solution. Any question about any of that? Let me just go up here and do 14. Take a look at what that looks like. Oop. I don't think this will be terribly meaningful to me. You have a lot of water molecules. Oop, didn't do that right. So you have a lot of water molecules, but you only have one H plus in solution for 1 times 10 to the 14th water molecules. So numerically, this doesn't mean terribly much to me. All right. Any question about any of that? I guess I don't need to save that. So increasing H plus, increasing the acidity, lowering the pH from pH 7. You can go down as far as pH 0. Decreasing the H plus ions in concentration increases the alkalinity, raising the pH from pH 7 going up to pH 14. And like I said, I don't know why it stops at 14. Acidic solutions have more H plus ions in solution than OH minus. Basic alkaline solutions have more OH minus solution, ions in solution than H plus ions. Most organisms grow best around pH 7, meaning most organisms grow best between pH 6.5 and 7.5. Any question about any of that? All right, let's talk a little bit about acids, bases, and salts. An acid is a substance that disassociates, giving up one or more H plus ions in solution. Like HCl will dissolve in water, giving off H plus ions and Cl minus ions. And that will increase the H plus ions in solution, why we call HCl an acid. Any question about any of that? A base is a substance that dissociates, giving up OH minus. And this is the textbook definition, meaning your author's definition of what a base is. Like sodium hydroxide, you dissolve it in water, breaks down into sodium ions and OH minus ions. This OH minus ion will increase the OH minus concentration in the water, making the water more basic. All right, here's a question for you. If you dissolve HCO3 ions in solution, it will break apart into H plus ions and H2CO3 so that excuse me, I didn't say that right. The HCO3 minus will absorb H plus ions in solution to become H2CO3. That will reduce the H plus ions in solution. Everyone see that? So is HCO3 a base? Anyone? HCO3 is a base because it decreases the H plus concentration in solution. It'll make the water more basic. So HCO3 is a base, even though it does not disassociate, giving up an OH minus. So the correct definition of a base is something that either gives off OH minus ions or something that absorbs H plus ions in solution. Any question about that? And you have to get that from this lecture because your textbook does not discuss a base absorbing H plus ions in solution. Any questions about that? All right. Salts and electrolytes. A salt is a substance that dissociates into a cation, that's an ion with a positive charge, and an anion, an ion with a negative charge, neither of which are H plus or H minus. Like sodium chloride is a salt because when it dissolves in water, it will become sodium ion plus 1 and chloride ion minus 1. So sodium chloride is a salt, and everybody knows that because we call sodium chloride table salt or just salt. However, magnesium chloride, which would be magnesium, 2 magnesium chloride, no, it's magnesium plus 2 chloride ions will break apart into magnesium plus 2 and then 2 chloride ions, is also a salt by chemistry. So a salt is something that just disassociates into a positive ion and a negative ion, and that name is a cation and an anion. Salts are electrolytes. An electrolyte is a molecule which dissolves in water and then can help carry an electric charge. Like sodium chloride, when it dissolves in water, becomes salt water, and salt water can carry an electric charge much better than distilled water. And that's why when you're swimming in the ocean, if there's an electric storm, meaning a lightning storm, you should get out of the water because if the lightning were to hit the ocean, anywhere near you or even not that far away from not that near you, the salt water can conduct the electricity and that could be dangerous to you. Whereas if you're swimming in pure water, which you don't ever have distilled water, but natural water, it's not as dangerous because the electricity has to get really close to you. I don't know, within a few feet in order for it to transfer the uh, electricity from the lightning, that would be dangerous to you. If it were hit on the other side of the lake, it wouldn't be dangerous to you. Any question about what an electrolyte is or a salt? All right, let's briefly talk about organic compounds. Organic compounds are compounds that always contain carbon and hydrogen. The simplest organic compounds are called hydrocarbons, and they only contain carbon and hydrogen. Let me see if I can blow this slide up. So methane, ethane, propane, pentane, these are all hydrocarbons, and they only contain carbon and hydrogen. That's why it's called a hydrocarbon. There are other organic compounds that do contain other elements other than carbon, like acetic acid has some oxygen. What is this substance? This might be a phospholipid. Has oxygen and phosphorus in it. There's oxygen there and oxygen there. So that's an organic compound that does have carbon. In fact, carbon and hydrogen are the main atoms in this molecule, but does have other atoms as well as oxygen and uh, phosphorus there. So this is an organic compound, but it is not a hydrocarbon. These are hydrocarbons. These are hydrocarbons. We'll talk about those a little later. Organic compounds always contain carbon and hydrogen. They may contain many other elements, especially nitrogen, sulfur, phosphorus, and oxygen. So many of them actually contain oxygen. Not all organic compounds contain oxygen, but many of them do contain oxygen, and they may contain other atoms as well. They're all held together covalently by a chemical covalent bond, usually the carbon holding most of the molecule together. So like this organic compound, all of the atoms, or I should say most of the atoms, are being held simply by the carbon backbone holding the molecule together. Obviously, right there, we have an exception, and right there, we have another exception, but most of the molecules are held together carbon to carbon. Any question about any of that? Compared to an inorganic molecule, organic molecules are more complex and they're capable of more complicated biological functions. Some examples of an organic compound include carbohydrates, nucleotides, lipids, and various hydrocarbons. Organic compounds always contain carbon. Carbon is important because it can bind to four other atoms, like this carbon here is bound to four other atoms. Carbon atoms often found bonded together in a chain or a ring structure. So there we have a chain, carbon holding the molecule together, carbon backbone. Let me go here. This is a bigger picture. So here we have the carbon holding the molecule together, carbon backbone holding the molecule together. Here, wherever we have a point is a carbon. And once again, the carbon is holding the molecule together. Coming off of this point that's not shown are hydrogens. And this is a ring structure. That's a linear structure. Any question about any of that? All right. Organic compounds can have functional groups which bind to the carbon backbone. And a functional group is something like that, which gives the molecule additional properties. So this molecule, having the OH on it, will have additional properties to the molecule methane, which would have a hydrogen right there. And that functional group is the OH functional group. It gives this molecule different properties than methane, which would only have an H there. For example, methane is a nonpolar molecule. It does not dissolve in water. Methanol, having the OH group, functional group, is a polar molecule. This part right here is polar, and methanol can dissolve in water. Any question about that? So the functional groups give the molecule additional properties and behaviors. Nope, I don't have that right. Functional groups are responsible for most of the chemical and physical properties of a particular organic compound or molecule. So of the organic molecules, most of their properties come from the functional groups. A functional group is something attached to the molecule like OH, which you find in alcohols. It's hydrophilic, so attracts water molecules to it and helps dissolve the alcohol in water. So the first functional group we're going to talk about is the OH group. It's called an alcohol. You can find it in lipids and carbohydrates, and actually it's found in many organic molecules. Like it's found in glucose, it's found in starch, it's found in lipids, it's found in proteins. So you can find that all over the place. These are different organic functional groups. You don't need to know about them unless they're surrounded by a red box. This is the amino group, NH2, when bound to a carbon. That's the amino group, and that you find in amino acids and proteins. The next functional group we're going to talk about is the carboxyl group. That's the C double O bond and then an OH, and sometimes it's called COOH group. It's the carboxyl group found in organic acids, lipids, and proteins. Let me blow that up a little. So you can find this in amino acids, the COOH group, proteins, lipids, etc. This is the phosphate group, that's PO4, and that oxygen here and there actually has a negative charge. This is a phosphate group found in ATP, DNA, and RNA. You must be familiar with the groups shown in red boxes. And why do you think I want you to know the groups shown in red boxes? What's common about that group and maybe that group too? Anyone see anything familiar with these groups? How about this group here or that group there? These groups are the groups that are important in biological molecules, so you must know the functional groups surrounded in red box. And frequently, more than one functional group can be found in a single molecule. Like with an amino acid shown below, we have an amino group on the amino acid and a carboxyl group on the amino acid. Any question about any of that? All right. Organic compounds can have small organic molecules combined to make a larger organic molecule. The small organic molecule we call a monomer. The large macromolecule or large organic compound we call a polymer. A polymer is a macromolecule composed of many small repeating molecules called monomers. Any question about any of that? Let's give an example here. Let me go ahead and give a real example. Starch is a polymer composed of many monomers. The monomer that makes the starch, all of the monomers are glucose. That's the only thing you find in starch. So that's an example of a polymer being starch. It's a macromolecule, very large, and it's held together simply by repeating glucose units. Organic compounds can be made by dehydration synthesis, where you take an R group, which is a monomer here, and another R group, which is a monomer there. You pull off water, meaning you pull off OH from this R group and that hydrogen from this R group. The hydrogen gets together with the OH to make water, why it's called dehydration synthesis. And then the two R's bind together, which it's called the polymer here. It's really a dimer because there's two monomers binding together. This is also called the condensation reaction because the RR group is larger than either ROH or RH group here. And then you can split the polymer or the dimer here by adding water and then going this way in a reaction that's called hydrolysis, where you add water. The water then splits apart with the OH group going to the R there and the H group going to the R group there, forming the two monomers. So dehydration is a mechanism for synthesis of macromolecules such as carbohydrates, lipids, and proteins. Hydrolysis is the breaking down of the larger molecule to form a smaller molecule by adding water. So this is showing you a dehydration synthesis, where here we have a small polymer, and it's going to be adding a monomer. The OH group comes off of the monomer, the H group comes off the polymer, forming water, and then that monomer binds directly to this polymer with a chemical covalent bond. And then hydrolysis is adding water to split off this monomer from that polymer. And then the water breaks apart with the OH going on the monomer and the hydrogen going on the end of the polymer. And that is hydrolysis. These reactions go on all the time in your body, by the way. For example, our liver stores glucose as is a glycogen, something like that, which is a polymer. And when we need more glucose in our blood, we will add water in hydrolysis to break off the glucose, and then that glucose will join the blood, and then the polymer in the liver will be shorter. And then when you're eating more glucose than you're using, the glucose will be stored down in the liver where the glucose will undergo dehydration synthesis to form water, and then that glucose will be added to the glycogen to form a larger polymer. Any question about any of that? All right, carbohydrates. Let's talk briefly about carbohydrates. They include sugars, starches, and many other complex carbohydrates. Carbohydrates are an important energy source. They're important in your cell structure and your body structure. Carbohydrates are also important in nucleic acids. Carbohydrates always consist of carbon, hydrogen, and oxygen, but it's not just any carbon, hydrogen, and oxygen. It's specifically for one carbon, there are two hydrogen and one oxygen. And then for the carbohydrate, you just repeat that. So for like glucose, you have that N equal to 6, and there are 6 carbons, 12 hydrogens, and 6 oxygens in glucose. Any question about any of that? Simple sugars or strings of simple sugars linked together form the larger carbohydrates. So a simple sugar would be a monomer, which is a monosaccharide, and glucose and fructose are examples of a monosaccharide, which are monomers of the carbohydrate. You can then link two monomers together, two monosaccharides together, to get a disaccharide. Table sugar, which is sucrose, is a disaccharide, and it is formed by combining glucose with fructose to make the disaccharide sucrose. And then starch is a polysaccharide composed of many monomers. Starch is composed only of glucose hooked together one after the other to make the polysaccharide. And there's many glucoses in starch. Any question about any of that? All right, so carbohydrates, we have mono and disaccharides we're going to talk about. A monosaccharide is a simple sugar, always composed of between 3 and 7 carbon atoms. But most monosaccharides are either 5 or 6 carbons. Like glucose has 6, fructose has 6, ribose, another sugar, has 5 carbons. So almost all simple sugars have either 5 or 6 carbon atoms. Sugars or monosaccharides are sweet and they're water soluble. Why we call them sugars? Because they're sweet. Disaccharides are formed by joining two monosaccharides together in a dehydration synthesis reaction. Let me blow this up so I can show it to you. So we can have glucose, C6H12O6, shown here, and fructose, also C6H12O6, shown here, come together in dehydration synthesis, where H will be pulled off the fructose and OH pulled off the glucose. And then this carbon right there combined to that carbon right there, excuse me, that oxygen on the fructose binds directly to the carbon on the glucose to form the disaccharide sucrose. And then water forms. Why it's called dehydration synthesis. And then you can take the water here and split the disaccharide, where the water will break apart. The OH will join to the glucose. The hydrogen will join to the fructose. And then you can split this bond here, forming fructose and glucose. And that reaction you should know if you ever watch Back to the Future, where Marty McFly says, "Ma, you sure know how to hydrate a pizza." How she did was she took this black hockey puck, put it in her pizza hydrating machine, hydrated it by adding water, must be what the machine did, undergoing hydrolysis, and then out came this beautiful hydrated pizza. Any question about any of that? All right. Carbohydrates include the polysaccharides. A polysaccharide is a carbohydrate consisting of many monomers. Starch is the simplest polysaccharide, where it's simply a straight chain of glucose held together one after the other. You have many starch, actually more than six, that link together in a linear chain to form the starch. Some of the polysaccharides will have a branch chain like glycogen, which is how animals store glucose down in their liver. It's similar to starch. The difference is that the glycogen will branch, meaning that you'll have one chain here, and off of this one here, you'll get another chain going that way. So glycogen is similar to starch. It's just that the chain tends to branch. And actually, starch can have a few branches in it, but most of it's single linear monomers hooked together by a chemical covalent bond. Some other examples of polysaccharides are shown here. Bread, everybody knows is a starchy food. Cereal, everyone knows is a starchy food. Pasta, everyone knows is a starchy food. Rice, everyone knows is starchy food. Potatoes, everyone knows is a starchy food. Most people don't realize that beans actually are a very good source of carbohydrates, and chestnuts too. Beans are about 1/3 carbohydrate, 1/3 fat, and 1/3 protein, but 1/3 is an awful lot of carbohydrates. So beans are a good source of polysaccharides. Any question about that? And I think that carbohydrate is stored as starch in beans. Chestnuts, I don't know the makeup, but it's also made up of carbohydrates, fats, and proteins. But beans is very close to 1/3, 1/3, 1/3. Any question about any of that? Some other polysaccharides, cellulose is an example. Actually, cellulose is hooked together by glucose, held together one after the other. But here, let me show you if I can blow this up. Here we're looking at cellulose held together by glucose held together by one after another, although that bond holding it together is a little different than the bond holding starch together. And then the glucose forms a row, and there will be another row here and another row there and another row there of glucose held together. And all these rows get together, and then that glucose here will have a hydrogen bond to that glucose, and this glucose here will have a hydrogen bond to that one. And then this one, besides holding on to that one with a hydrogen bond, will hold on to that one there. And glucose, I mean cellulose, as you can see, has a lot of hydrogen bonds holding the glucose together. And that's what makes cellulose so difficult to digest. And humans, as you know, cannot digest cellulose. We cannot eat grass and get nutrition from it. The cow cannot either, but the cow has a microbe in its stomach, which actually has, uh, well, we'll just say it has microbes in its stomach, which digests the cellulose and then makes some of that cellulose available for the cow to digest. So that's why the cow can eat grass, and that is it has microbes in its stomach that digest the cellulose for the cow. Any question about any of that? We'll talk about peptidoglycan in a later lesson. I've already talked about glycogen, how it's a branching chain of glucose, and then starch, it's mostly a single linear change of glucose held together. Any question about any of that? All right, if there's no questions, I think I'll stop here because this is a good place to stop. And we will continue with this lesson. Oh, gosh. Oh, for this slide, let me state you don't need to memorize the slide. You just need to know that it's for illustration purposes only. Hopefully, I'll be able to find that. All right, any questions?
Yeah, I got a question. What
What?
for our quiz, what chapters will they go over?
Are you talking about the quiz for next week or because the quiz for this week was actually on Wednesday.
No, no, for the next week, the main quiz.
All right, on my syllabus, which is shown here, I hope you can still see it, um, shows that for quiz one, which will be next Wednesday, it'll cover chapter one, chapter 10, the start of chapter two, what we covered today, and then lab 0, 1, and 2. So on the syllabus, I state what the quiz covers.
Okay, thank you.
All right. All right. No further questions. I'll see you at 6:30 for the lab.